Okay, so did you enjoy the Beer's law lab, the absorbance one?
Yes, but also I feel like I don't really understand absorbency well enough.
So now a couple key things about the Beer's law is that first, like I said, like I explained it last time. Should you use your hand to touch the cuvette?
No, because of the oil.
The oil increases the absorbance, so it will jack up the concentration than what it's supposed to be. So we don't want that. And also, how do you decide the wavelength of your absorbance? We decide the wavelength of your of the spectrometer, spectral photometer. How do you determine the proper wavelength? Yes, and also you always want to look at the graph and see which wavelength has the highest absorbance, and you would use that as your wavelength. Okay, and of course we will use a few standard solutions to make our best fit line, and then the equation of the best fit line will be used to determine the concentration of the unknown solution. Uh-huh.
Labs.
Mm-hmm.
She said there's gonna be lab questions on
there. Uh-huh. So for the collection of gas over water, so one major question that I would definitely ask, okay, is that when do you stop collecting gas, and why? And what do you do with the? How do you find it? Making sure that you have to subtract the water vapor pressure from the barometric pressure. Yeah. So you want to get the partial pressure of the hydrogen from the total pressure by subtracting water vapor pressure from the total pressure. And then for the Beer's law, like I said last time, look at all the errors. Okay, and one major error is to touch the cuvette without using your Kim wipe or the paper. Yeah, the blank, your zero basically. All right, just send me a picture, right? So it says that's nice handwriting.
Yeah, because Zuber has really good.
Okay, a 3 gram sample of brass is dissolved in nitric acid and diluted to 150 milliliters. The solution has an absorbance of 0.4. What is the percent mass of copper in the sample? And I assume that they give you the graph, yeah? I can see the picture. I'm just making sure that the graph is not something that we need to know. So if you know let me go ahead and drop it over here. So if you know the absorbance, that means you would know the concentration, which is 0.2, right? Now, so what it means, okay, now this is like pieces of dominoes. If you know your concentration of copper and you know the volume, that means you can get moles, okay? And if you can get the moles, that means you can get the mass.
I got it. Yeah, moles times molar mass.
It's mass. The good old Chem 1 stuff. Okay, having units would be better. Yeah, so you got the grams, and therefore, and the total mass is 3 grams, right? So that means out of the 3 grams, you have 1.91 grams of copper. And that's how you know the percent of the copper. So the key point of this question is that when you know the absorbance, what is the next immediate information that you can tell? And you keep pushing, basically. You know molarity, and if you know molarity, what else do you know? You know the moles, because you know the volume. Yeah. And if you know the moles, that means what else do you know? You know the mass. And if you know the mass, how does it help? Well, you can get the mass ratio. So that's how you push the boundary, basically. Okay. Any specific questions on the review? So this is what I said, I think 2 weeks ago, right? So there are 2 types of Boltzmann distribution right here. Boltzmann-Maxwell distribution. One, same gas, different temperatures. The other one, same temperature, different gases. So the way to spot out the different identities of the graph is that, well, you basically look at the peak to determine who has the greatest speed. And, well, hotter gas molecules would run faster. Lighter or less mass, or gas molecules with less mass, they run faster. So that's how we will decide these temperatures. No problem. Okay. Oh, wait. Sorry, my bad. Yeah. Yeah. I forgot to read the x-axis. This is the fastest. Faster right here. Slow here.
Wait, this is the fat thing you was telling me yesterday.
So faster is 400K, 350K, 300K, 250K.
So the top curve has the highest molar mass.
Oh no, this is the same gas at different temperature. The next graph, same temperature, different gases. So fast.
And this you have to
slow.
molar mass.
Yes. So H2 would be the fastest. I believe F2 would be the slowest. O2 would be the next, and then CH4 is the second fastest. Okay. So very easy, very easy. You said which question again? Number 5. Okay. Oh, so what's the molar mass? So for molar mass, that means we need to know grams per mole, right? So grams per mole. So do we have grams? Yes, we do. And it's STP.
Yeah, so
1 mole is equal to? Okay, so change this to 0.25 liters. So 0.25 liters times 22.4 liters, 1 mole over that. Then whatever the moles you get, that shall be the mole in the denominator. Now there is another equation that you can use, but I like to do it this way because you don't have to memorize that. You don't have to memorize the other equation. The other equation that you could use is the one that I don't even remember firmly. So whenever I need to use that equation, I just go ahead and derive it. So P, mass over volume, is density, and then mass over mole, it's molar mass over RT. So
we didn't do this.
no, sorry, my bad. It should be D over P. Sorry, D over P. D over P.
I remember asking you about this.
So D RT over P would be your molar mass. So you could actually put these two together to get your density, and then you know your R, you know your standard temperature and pressure. That works out just fine. So either way, it's fine. I wouldn't say one is better than the other. Just make sure that you know what you're doing. But I would say if you know the old school way, that would be brilliant. Okay, so 0.7 divided by 0.0112, then the molar mass is equal to 62.5 grams per mole. Cool. All right. Okay, so we have the moles of argon, we have moles of CO2. So the question is really about partial pressure of CO2. It's the same thing as the mole ratio of CO2, which is 3.5. Well, actually, I mean the mole ratio of CO2 times the total pressure. That's what I meant. Okay, so 3.5 moles over 5 moles total times 7.3 ATM. So 5.1 ATM would be the partial pressure of CO2. Okay, so whenever you see a bunch of gases, then well, I would quickly relate to partial pressure, which would also relate to mole fraction.